Today I'm going to present a work that has been done in my group under my supervision. And that's why the first name is the name of the PhD student who did the actual work. Okay, I'm Michel Perez, and I am working at INSA Lyon. So my talk will be divided into mostly, I would say, 3 parts. First, I will introduce a little bit my group, my lab, MATEIS. Many of you maybe do not know this group, which is okay. And then I wanted to talk about a few tales that I often encounter in some introductions of PhDs. You know, when I have to review some PhDs, in introductions, there are often things like, oh, I want to enlight materials, so that's why I do this research and this research to make lighter cars and lighter planes, and this is my motivations. So I would like to come back on these, which I call tale for, not for nothing, okay? And then I will enter into the subject of dual phase after introducing what these kind of steels are and what they are for, okay? Just a quick remark before we start. I planned something like 40-45 minutes talk, but I feel better if you ask questions while I'm speaking. So don't worry, even if I don't have time to finish, I will cut the last part. It's not such a big deal. What is important is that we interact as much as possible. So don't hesitate to ask questions, interrupt my talk, and pose any question you like. And don't worry about the timing. I promise at 3 o'clock, you're free to go. Okay? Shall we go? First of all, yes. I can introduce the MATEIS group, which is quite a big group, 200 people. I don't know if it's big. Nowadays, we don't know what is big and what is not big. So MATEIS group is approximately 200 people, and the strategy of the group is to connect the process, the microstructure, and the properties. And if we are able to better understand these 2 horizontal blue arrows, then we can eventually perform the feedback loop of optimization. And our favorite tools are some characterization and modeling tools. So there are some quite historical characterization tools that have been developed in the group, starting from the left, small angle X-ray scattering, essentially for polymers, to really detect, for example, for semi-crystalline polymers. Then thermoelectric power to measure the evolutions in the microstructures of metals. X-ray tomography, and very small here in the picture, this is the head of the lab, Eric Mayer, who was famous in this lab here at LMS because he used to work a lot with Michel. Some of you may know Michel. Some of you may not, I don't know. So this guy was really, they were really working together with strong connections, us doing the 3-dimensional analysis of, and you doing the mechanical modeling. And there was quite a nice history of collaborations between MATEIS and LMS with this technique. And of course, at the right, electronic microscopies, transmission, scanning, and all these techniques. In parallel, I'm going to change my slide. In parallel, it's a bit more recent. We developed many simulation tools to better understand the build-up of the microstructures of materials and also the mechanical properties. So this graph is something you saw 1,000 times. And these tools are the ones we are developing at MATEIS from the atomic scale. Some of you have something, a stick or something? Maybe?
No.
Yeah, so from ab initio simulation, molecular dynamics, coarse-grained molecular dynamics to study, for example, block copolymers, to finite elements passing through atomic kinetic Monte Carlo, and all these kind of simulation techniques that we are developing. So within the MATEIS group, there are a few teams. One studying polymers, one studying ceramics, one studying metals. And here I will present my team, the one I know better. It is the metal team, the team, the group of people studying metals. So we are approximately 60 people, including everyone, with a majority of PhD students, the one who are actually doing the research. And here are some numbers that you can read if you want, concerning the metal team in MATEIS. Any question? Okay, so in the metal team, what are we doing? So we have mostly three main activities. The first one is elaboration. So how to build, oh, that's great. Super. Excellent. Thank you very much. First team is elaboration. So we are building some graded materials, studying sintering, welding, and we recently bought arc melting and atomization, and which is coupled to robot casting. So we can do some nice materials with nice structures. So in parallel, there are people working in what we call physical metallurgy. In fact, this is the understanding of build-up of the microstructures. And one group specialized with studying the mechanical properties, because most of the materials we study in the metal group are studied for their mechanical properties. Okay? We are more and more doing some very specific elaborations for also some other properties than structural properties, for example, biocompatibilities and so on for biomaterials. But basically, this is the DNA of our team. So what are the characteristic equipments that we have in the metal team? Techniques to characterize the materials. As I said, specific techniques that I presented, and simulation techniques that I also presented. So this gives you quite a quick overview of what we are doing in the team. Any questions? Okay. So as I said, there was a quite interesting history of collaboration. I think it stopped because of the departure of Michel. It can start again, of course. So the motivation of this work, this PhD work that I'm going to present, is, of course, to improve the properties of what we call the body in white of a vehicle. So the body in white is, what could we say? The bones, the backbones of a car here, that is made of metal. And as you know, if we improve the fabrication process, eventually we can have lighter materials. And this is our business, how to design, how to make lighter materials. And of course, there is this big question, do lighter materials lead to lighter vehicles? Because that's the motivation. We often mention the greenhouse gas emissions. Of course, if we have lighter vehicles, we save gas and then we save CO2. In fact, this question is not so simple, as you will see. And this brings me to my tales that I wanted to present. The first tale is that progress in material science make cars, you can say planes, is the same, lighter. And in fact, if you look at the numbers, you see that it's the average mass of vehicles, and this is the time, and you see that cars, even they are not lighter, but they are heavier. What a failure. So what went wrong? We are making lighter materials for sure, I promise. And you are also maybe doing the same. And at the end, with lighter materials, you build heavier cars. That's a big question, isn't it? So first aid, people say that if you lighten materials, you will end up with lighter vehicles. That's wrong, obviously. So there is something wrong here. Maybe we can discuss that later, but this is an interesting point to present. The second one is that, thankfully, we live in the EU. We don't live in Australia or in USA, where there are no rules. In the EU, we have some rules, and we have some standards in terms of fuel efficiency. And in fact, yes, it's true, but not as we can imagine. Here is the European Union standard. Here is the emission that you are allowed to make if you build the car. And here is the weight of the car. And what you see, which is surprising at first glance, is that, yes, there is a standard. But this is not an horizontal line. This standard depends on the mass of the car. So the heavier the car, the more CO2 you are allowed by the EU to emit. That's strange, isn't it? So if you are a car builder, would you go there, or would you go there with twice the margin that you have here? So obviously, it's better to go there. So there is no rules to make, in fact, cars lighter. So, third thing, recycling. And oftentimes you go to conference when there are industrials that are invited. I remember at SF2M, and there are a lot of industrials saying, oh, don't worry, we recycle almost 100% of our production. That's fantastic. There is no problem. Okay, recycling. Let's go a bit deeper in, let's stay in the car market, okay? So let's imagine that we are in 2019, and let's assume that this car market has a growth per year of 3%, which is quite reasonable. So each year, you have 3% more cars than you have the previous year, okay? So in fact, this is the actual fleet of cars, and each year there is a bit of these cars, the blue part here, which are dead, okay? And each year there are these new vehicles in red. And the difference between this year and this year is only 3%. So let's zoom a little bit. So all these end-of-life vehicles, let's say that we recycle the steel or the aluminum or all the materials up to an amount of 95%, which is really a nice number, 95% of recycling, okay? So you recycle 95% of end-of-life vehicle, but at the same time, you have to build new cars because of the market, which is growing 3% per year. So at the end, if you compare the new cars you have to build and the end-of-life cars, and then this 95% of recycling, you still have half of your production each year, which comes from raw materials, not recycling, because there is not enough old cars to recycle, okay? So recycling, for me, my point of view is that recycling is a tail, okay? Or at least you have to know about these kinds of numbers. Okay, the last one. Oh, sorry, yes?
I was simply wondering on the major market, like I suppose European market, car market, is in the long run an increase in the number of cars reasonable? I mean, if we assume that the number of cars produced is going to stabilize, which To me, I don't have figure, but to me, it's not complicated. It would be far less of a problem.
Exactly. I mean, all the problem of recycling that I explained is due to the fact that the market is growing. If the market is plateauing, but I think that's a conclusion we can have on all human activities. If you are happy with what we have, then we have no problem. The problem is that we always want more, and we always produce more, and we always earn more, and we always more and more, okay? And that's the source of the problem, maybe. So the last and fourth day is, oftentimes you can read in PhD introductions, aluminum is lighter than steel. Okay, that's true. Aluminum may be lighter than steel. But first you have to account for everything, the whole life cycle of the material. And here we compare 4 different solutions. So the baseline is the actual made cars, okay? During the production, the life of the car, and the end of life of the car. Okay, so this is the baseline. And either in energy or in CO2. You see, it's quite the same. Then we compare this actual scenario with 3 different scenarios. One scenario with extensive use of high-strength steels, the one that I'm going to develop. Okay? One with the extensive use of aluminum, and one with the extensive use of composites. What you see is that, yes, aluminum is lighter than steel, and that's why during the life of the vehicle, then aluminum is gaining some CO2 compared to steel. The problem is that to produce aluminum, and that's something we have to take into account, you have to spend much more energy, okay? And to produce composite, it's even worse. So at the end, you see, it's interesting. At the end, if you assume that the life of a vehicle is 200,000 kilometers, it's ex aequo. Yeah?
But why the total energy for the AHSS is negative at the beginning with respect.
Oh yes, it's a little, let's say, the same. It's in fact because improving the way we produce steels, high strength steels, you save a bit of energy and CO2 producing them, but it's, let's say, it's 0. It's non-significant. Okay. So the conclusion of this chart is that okay, making cars with aluminum is interesting only if you keep them for more than 200,000 kilometers. Okay, always there is something good and something you have to consider. Okay, now it's time to enter into the details of what are these high strength steels that I'm going to present today. And I'm going to present one example, which I call dual phase steels. So dual phase steel is a mixture of hard martensitic steel with soft ferritic steel. And you know, I'm not going to learn that to you, that if you mix a hard phase with a soft phase, eventually you can combine the advantages of both. For example, here is the tensile properties of martensite, here is the tensile properties of ferrite, and of course you end up with something which is in between. It has quite a high heat strength, while having also some ductility. So these dual phase steels, they are produced classically using this temperature time route. First, we go into the intercritical soaking domain to have a mixture of austenite and ferrite. Then we quench, the austenite transforms into martensite. And then eventually we perform aging treatments, and we would like, the aim of this work is to understand, predict the effect of each stage of the treatment on the today, that's what I'm going to present, is what is the effect of this soaking treatment on the mechanical properties, and eventually what is the effect of the quench on the mechanical properties. So mostly there will be 3 parts to this talk, and don't worry, if we don't have time for the 3 parts, there will be 2. It's not a big deal. The first is the study of what's happening during this intercritical soaking. In fact, when you heat, it's fully ferritic and then turns into a mixture of ferrite and austenite, and we would like to have a model to model the kinetics of formation of austenite. Then we would like to have another model to predict the martensitic start temperature in order to know at which temperature this transition occurs and solute atoms cannot diffuse anymore in the signific matrix. And eventually, we would like to know what's happening during tempering of these martensites. Okay? So let's enter into the modeling of alpha to gamma transformation. And recall, this is what happens in dual phase steel when you heat and when you wait in the intercritical domain, where you have both at equilibrium, ferrite and austenite. So there are some existing models. I'm not going to enter into details. The most famous is Dictra. Maybe you know Dictra. It's the friend model of thermocalc that you may know. But Dictra is based on local equilibrium, means equilibrium at the interface, which is not always the case. There are some other more elaborated models. Maybe the most elaborated one is phase field that some of you may know. So what we did was we designed a new model which would take a bit of each of them, take only the advantages. So the idea is to have a thermodynamic database based on thermocalc, that we do not require any special equilibrium condition at ferrite-austenite interface, and a model that obeys a simple experiment principle, which is the direction that it will take is the one that minimizes the Gibbs energy function. That's why it's called Gibbs energy minimum model. So it will choose the minimizing direction to minimize the Gibbs energy. So to build this model, we start with the first model, which is extremely well known and nothing new. Just we model the fact that diffusing element, a solute atom gradient, will naturally transform into a flat profile. So first ingredient, diffusion. Diffusion of, for example, carbon or manganese or any kind of solute elements in the steel, in both ferrite and austenite. First ingredient, diffusion. Second ingredient, remember, we want to model the transformation of ferrite into austenite. So we have a moving interface, and we want both phases to be described with an interface. So if you have an interface, you cannot use this classical Fick equation. You have to transform it into an equation where the diffusion is a function of the chemical potential and not only the concentration. So we have to slightly transform the diffusion equation, and let's say that the interface is seen as a chemical potential variation. If you have, for example, austenite on this side and ferrite on this side, the chemical potential is a step function like that. We can have an interface which has a certain width, and eventually we can have an interface with this kind of potential well, accounting that solute atom may prefer to locate at the interface. So once we have included this ingredient, let's see what happens when you start with a constant concentration profile, but with a chemical potential that makes a step. So what we end up with, it will end up with the concentration, which is higher in one phase and lower in another one. And if you think of iron carbon, for example, you know that carbon solubility is much higher in austenite than in ferrite. Okay, so that was the second ingredient of the model, the modeling of an interface with two different domains. Okay, third ingredient, now we want this interface to move. And to make this interface move, we start with gamma here, the austenite, alpha, the ferrite, and we move the interface in the direction and with the amplitude that minimizes the Gibbs energy. So simply, the movement of the interface is the one that will minimize the Gibbs energy. So if the interface is here, the model is going to check that, oh, okay, if I move it here, will it minimize the energy? No, okay, I don't move it. If I move it here, one step backward, will it minimize the energy? Yes, no. And we choose the position that will minimize the energy. And we can have one interface between austenite and ferrite, but we can also have two interfaces between carbide, austenite, and ferrite, because I'm not going to enter into detail, but sometimes presence of these carbides completely change the kinetics because they can store a lot of solid atoms. Anyway, what does it give? So here I plotted the overall transformation kinetics. So it's the austenite fraction that you can see evolving as a function of time. And that's a fairly strange. So it's during an isothermal treatment. So you start at a given temperature. So it's at 750 in the intercritical domain, and you suddenly start from 100% ferrite, and you suddenly hit to 760, for which the equilibrium will be 70% austenite and 30% ferrite. And you see that there is this strange evolution. But this evolution is due to many things occurring at the same time. And we can understand, and this is what the model predicts, only if at the same time we plot the carbon concentration profile and the manganese concentration profile. And the whole complexity of the problem is due to the fact that one guy is diffusing extremely fast and one guy is diffusing much slower, okay? 10,000 times slower. So what happens? Let's analyze what happens. During the first quite quick step here, you see that the carbon profile is building, almost the equilibrium profile during this fast transformation. And while the carbon profile is building very fast, you see that manganese profile is not evolving up to a given time where you start to have this high and low concentration in ferrite and austenite. And then at the end, so here, the interface is here. It's going too fast for the profile to build up. Here, the manganese is diffusing, and then there is an equilibration of manganese within austenite. So this is what explains fast, only carbon is moving, then manganese is moving in the ferrite, and then manganese is flattening in austenite. This is why you see this go back to the equilibrium. Okay? Any question concerning this stages? Yes?
I'm not sure exactly what is the initial condition?
So the initial condition is 100% ferrite, but there is a tiny, very infinitely thin layer of austenite with one interface. And we see this interface moving versus time. So the equilibrium, the initial condition is the one that was shown here. You see, there is austenite, but there is a very almost zero, just one layer of austenite. Then we have the interface, and then a lot of ferrite. And then suddenly I hit to 760. Does it answer your question?
Yes. I have a question. It seems that in the third plot, you have a creation of an interface there.
In fact, no. The interface is already there, and you can see where the interface is at each. But what what happens here is that the interface moves, but the manganese has no time to diffuse. So the interface moves, and manganese is flat. This is what we call para-equilibrium. It means that only carbon is at equilibrium, but manganese is the same before and after in ferrite and austenite.
What is the triggering? What is the triggering reason that at some point it starts there? Is there some specific something?
No, in fact, the trick is the log scale. So if we advance more and more the log scale, then manganese at the end has time to diffuse. In fact, the whole thing is the characteristic time for manganese to diffuse. And here, there is no time for manganese to diffuse, but here in this domain, manganese has time to diffuse. And that's why you see the interface. It was there, but you could not see it looking at this graph. Okay?
So you have ferrite and magnesite, so they have different composition in carbon?
Yes, in fact, at equilibrium, ferrite and austenite, at equilibrium, this is at equilibrium, this is the composition of austenite, this is the composition of ferrite in carbon, and at equilibrium, you will see in the manganese graph, this is the composition here of ferrite, and this is the composition here of austenite. This is what thermodynamics can do, phase diagram. But in fact, it takes some time to go from 100% ferrite to the equilibrium. And it's interesting to know where we pass to go from 100% ferrite to equilibrium. And it's interesting to have a tool that will predict the actual path that is chosen by the system. The path that is chosen by the system, from our point of view, is the one that minimizes the Gibbs energy or maximizes the production of entropy. For those who love thermodynamics, it's the same. So here we compare the model that we just discussed with a classical formalism, and we compare the profile. We see that they are almost the same. That's the thing to remember here. Or just, if I want to be mean, I can underline that ITRA does not respect the mass balance. So ITRA is not in agreement with Thermocal, which is strange because the same company is selling the two modeling tool. That was something that was funny because Thermocal model is here and ITRA ends up with a different value at the end, which is not the case for the fixed energy minimization model. Okay, so now that we have this tool, we can study interesting features, like for example, the amount of manganese in the steel, and you can remark that starting from a very low manganese steel, you have a very fast transformation kinetics, and if you increase manganese, there is some kind of threshold here where you end up with a kinetics, transformation kinetics, which is much slower. And for the industrial partner, this was quite interesting because they wanted to know how long, at which temperature, we have this many fraction of transformation. So this kind of graph is interesting for them. Okay? And the model was also checked on other systems, many systems where we studied the transformation kinetics for very famous experiments performed by other researchers. Okay? So we also did some more complex treatment, which is more like the industrial one, where you have heating and then isothermal. And we see that during heating and isothermal, the transformation stops and continues. So it's interesting to see what is happening during heating and during the isothermal treatment. So you see that during heating transformation of that, and then it continues while you are at the same temperature, and then eventually when you heat up again, it starts again to transform. And what is important is that during this isothermal process here, the transformation continues and we have manganese partitioning. That's very important for the kinetics of the transformation. Okay, so now we have a model to predict what is the fraction of austenite, which we transform in martensite or in quench, and ferrite. But that would be nice if you would have another model to predict what we call the MS temperature, which is the temperature at which during the quench, ferrite austenite transforms into martensite. Okay? So there have been many studies to guess, depending on the steel composition, the martensitic start of the steel. And what we could do is do some experiments and measure the dimension of the part in the Global thermomechanical simulator, which is, let's say, this is a tensile machine able to heat samples. And if we measure, so we have to imagine that we start from high temperature, and depending on the cooling rate, either you form cementite or you form martensite if you quench fast enough. Okay? And thanks to that, we could plot an experimental TRC diagram. And the aim now is to be can we model the whole diagram. And I'm going to start today with only how to predict the martensitic start temperature transformation. So, as I said, there was many models, many different models, which were working quite well with the 100% austenitic steels, of course, because they were designed for this composition, but the model completely failed to predict the martensitic start temperature for dual phase steels with the mixture of austenite and ferrite. So why? First, we better understand this disagreement. We choose the model that was I would say the best that we found in the literature, which was based on some thermodynamics, which could predict MS temperature. So this model was working fine for 100% austenite, but for dual phase steels, it was failing. So why? Oops, the other way. So this is the martensitic start transformation temperature that is predicted by classical models. And this is the experimental value. There is a nice agreement, but the problem is that for 60% austenite steels, the experimental value is here. So we have to account for a few things. The first thing is to account for the grain size. Okay? It brings us here to here. Okay? And the second thing is to account for the carbon concentration, which we can calculate thanks to thermodynamical calculations. So it's okay for 100%, but it doesn't work. We are still not here for it doesn't work for the 60% austenite steel. So to make this model reach the actual true line, we have to account for the actual manganese content, not the one given by equilibrium, the one that was given by the previous model at the interface. So we have to enter not the global manganese composition of the steel, but the local composition at the interface. And if we enter this particular composition in the model, then we can make it fit to the true martensitic start transformation. So, accounting for the local composition of manganese that we took from the previous model, we could get a nice agreement for martensitic start temperature. And now, last part of the talk, and I'm going to be quite fast because it's something that you better know, it's mechanics. How do we model the mechanical behavior of a composite of ferrite, soft, and martensite, hard? You know that there are some laws when you mix the hard phase and the soft phase. You know iso strain, iso stress, maybe you know iso work. These are the three classical laws that are used, but there are many others. And what we want, in fact, is to have the global behavior. We adapted an existing model from Alain et Anne, with the researcher at Nancy. So first, we take a constitutive law for ferrite. So this constitutive law, I'm going to go quite fast because it's something that you know. It's a Cox-making extreme classical law where you have the contribution of kinematic hardening, the contribution of the forest hardening, and the base stress Piles force plus solid solution hardening. So here are all the equations that you need for this classical Cox-making extreme approach, where you have this law that combines all the stresses. You calculate the forest stress due to the dislocation density here, and you have an equation of evolution of the dislocation density as a function of strain with annihilation and multiplication term. This is nothing new. Cox-making extreme, let's say these kinds of models are, I don't know, maybe someone in the 50 years. No. Extreme is not so old, but Cox-making these are quite old contributions. So if we parameterize the model, you can fit the tensile behavior of fully ferritic samples. Okay, so ferrite is okay. Now martensite. So for martensite, we use a slightly different model. In fact, here the equations are not much too small. We don't care about the equations. What is interesting is the basics. So we say that martensite is a mixture of many, what do we call them? Elementary units that are combined together. These elementary units have a purely elastoplastic law with yield stress that is distributed like that in this yellow function. So there is an infinity of elements with distributed yield stress. And it's kind of mimicking what is happening in reality in martensitic. So you know that martensites are needles. Some of them are very tiny, some of them are larger, and the local yield stress of one needle depends on its size. So you can assume that it's distributed like that. And if you combine with a law of mixture that is in between isostrain and isostress, you can end up with an evolution equation that gives you the mechanical property of martensite. Okay? We don't have to enter into the details of these equations, but what is interesting is that it's to know on which basis it's built. And then, once again, fully martensitic steel, depending, for example, on carbon content, depending on manganese content, depending on the grain size, we end up with a model that works quite well for fully martensitic. And now we combine the two. What we noticed is that neither isostrain nor isowork works well. And if we want to understand what's happening, we have to look at the evolving microstructure using EBSD, where you can see the local misorientation, and you can see that at the beginning, for fairly low deformation, let's say that martensite and ferrite, they deform the same way. But at some point, martensite fractures. So imagine you have two percolating phases, one hard, one soft. For low deformation, let's say that they are both deforming the same way, isostrain. But apart from a threshold value, martensite is starting to break. So we are slightly going from isostrain to isowork. And this is what is new here. This transition between isostrain and isowork from the investigation of the microstructure led to a law of mixture, which is organized this way. So we say that if the epsilon is 0, then it's isostrain. If epsilon is, let's say, larger, smaller than 0.04, it's an hybrid law going from isostrain to isowork depending on epsilon of martensite, the deformation of martensite. So we start from isostrain, we end up with isowork law, and in this domain, it's this law that goes from this to this expression. And once we have the coupling between the deformation of ferrite and martensite, by looping on the equations that I previously presented, we can predict the stress and strain of the dual phase steel.
How do you pick the threshold between the two?
Sorry?
How do you pick the threshold between the two models?
In fact, the threshold is taken from microstructural observation. So this 4% is that we look in the CBSD maps, and we say that always for deformations that are under 4%, martensite and ferrite deform uniformly. So there is a uniform map. And above this threshold, there are some equation, non-uniformity. And that's this EBSD that told us that we have to introduce this 4%.
But is it the threshold the same for the full metal, or you also have a different thresholds depending on our?
That I don't know. In fact, for our materials, we noticed for martensite plus ferrite, we noticed that the threshold was 4%. Maybe for other materials, it can be different numbers. Okay, I'm not going that it's a universal threshold. It depends on the properties of each phase. So we end up with a constitutive law for both phases. Here is a graphical. So at the beginning, you mix with a vertical line isostrain, the hard martensite and the soft ferrite. At the end, this is isowork, so this is this mixture law. And during the hybrid domain, it transforms from a vertical constitutive law to this law. And this is how we build from this curve and this curve, we build this curve for the martensite. And this is the validation of the model for different levels, for different steels. Depending on the carbon composition, the manganese composition, different composition, and we checked that the constitutive law, the hybrid law, leads to a better description than what was usually done using a isowork law from beginning to the end. So what we check also, but that's another story, is that we could also predict what is happening during aging, modifying the amount of carbon that was in solid solution. You know that if you age a martensite, carbon will precipitate, and if you can predict how many carbon can go in carbide and leave the solid solution, you can predict the mechanical properties of the martensite and of the composites. Okay, this is the results of aging at different times. See the time and different temperatures, and we can predict quite correctly the evolution of the structure on aging. So it's time to conclude, and I promised to leave you at 3 o'clock. If I conclude, I talked about ferrite to austenite transformation kinetics model that was used as input parameter to predict the MS temperature, the temperature at which martensite starts, and from the knowledge of the percentage of each phase, we could build up a mixture of a hybrid law of mixture to account for, that is accounting for the fracture of martensite that was observed above 4% of deformation. So as far as outlooks are concerned, the idea would be to introduce the martensitic model, the quench model, into the transformation model to be able to model the movement of the interface back from the austenite, but this time to martensite. So this is quite complicated because this is not diffusive transformation now, it's displacing. So it's another physics. So we have to introduce another physics in the model, which is not based on diffusion. Maybe we have to introduce nucleation of martensite in this model. And of course, the holy ground would be to model continuously martensite, daylight, airlight, depending on the cooling rate, to have all the transformation rates that are possible. Okay? Thank you very much.